beginning. We were trying to take pictures too quickly, and the default libraries that you have on Android for this weren't designed for that. They were expecting you to take pictures much slower. So the code is now adapted to allow you that, but you can tweak it. Once you have the pictures, it very much depends on the machine that you want to use to do the learning, but it's a matter of a couple of hours if you are using the order of a couple of thousand pictures. And then the resulting file is a few hundred megabytes, give or take, and that's what you put on the SD card or the flash memory of the RoboCar.
Okay, so that's to train it, right? The couple of hours. How about when it's actually trying to make the decision?
The prediction is pretty fast. I really don't know, but that's a great thing to maybe profile.
You can drop off your question to us, so we.
Okay. Say it again.
I'm asking him to drop off questions to us, so we can get down.
Okay. Awesome. Should we wrap up the questions, or we have time for?
We have time.
We have time. Awesome.
Yeah. I have one question when you're done.
Oh, I will write to you in a second.
Is there so the recommendation is that we train the model, or do you already provide a trained model that we can use?
I could give you my train model, but it would only work if you run in the same tracks that I have, right? Because it's been trained for a specific track. As long as you're in the same track, you're good. But the moment the light conditions, the color of the pavement changes, the tape changes, the distance between them changes, then the model is not gonna apply anymore. Something we haven't tried is like to train the model with different tracks. That could be cool, for example. Lydia.
So you mentioned upfront, like computer vision is one approach, right?
Correct.
So like what's the Tango has depth sensor. There are other sensors. So what are ways in which you can improve the accuracy? And in your current model, like based on the data you have, what has been the biggest challenge in getting accuracy?
Awesome. So right now, the meetup in California, in Oakland, they're running these numbers. They've been doing it longer. They are a larger group. They've been running statistics on how fast the different methods that you just mentioned, TensorFlow, machine learning, computer vision, and humans are driving the car, right? And so once they've been doing this for a while, which one is working better? And right now, the numbers, I believe, the last time I checked, and Liam, I don't know if you have better numbers, humans are the fastest yet. Still, a person like looking at the tracks and driving it manually is able to do it faster than the car doing it with any autonomous driving for these RoboCar projects, right? Next is computer vision, next is machine learning. But the differences are closing. Every meetup that they do, and they do this every month, it's getting closer and closer, and they expect that at some point machine learning might be closer to computer vision. I say this because basically computer vision is well known, it's very efficient, it's very easy to understand, and it's so far the one that is the easiest to implement. Because you have more control about what's happening in the pipeline, because it's more intuitive. And that is actually a method that today, you want to use it, works very well out of the box.
But this is pure computer vision. It's not using any other third-party sensors.
Pure computer vision. And then machine learning is the one that is more challenging. How do you improve this? To answer the other part of your question, real-world cars will have LiDAR, will have some kind of sonar, will have other other sensors there. We haven't tried that. I haven't tried that myself. LiDAR is the one that I would recommend you to try next, because from a learning experience, it's the one that is the closest to the real world. This is when you see these self-driving cars and they have something on top that is rotating, that is a LiDAR. And classically, that has been very expensive and very difficult to include in a hobby project, in the order of thousands of dollars. But lately, there are a bunch of startups that are doing this in a way that is way more affordable. They are lower resolution, they are not as good as the expensive ones, but for a hobby project or a small indoor project, it does the trick. And we're speaking about hundreds, like 200-300, I've seen a few, definitely under 500. So definitely, if you wanted to improve it and get it closer to how real world works, in addition to a camera that is doing computer vision and possibly machine learning, you would add more cameras, because real world cars have multiple cameras, and you would add a LiDAR.
So I'll let other people take this, but the two things that came to mind was like, I forget what the sensors are in Tango, right? But the idea is like, especially when you're looking at race car tracks, when it's the same navigational path over and over again, at some point, can you make it optimal? You don't even have to look. It's like a person who's driven the same race course can drive it blind, right? So the only thing you're really looking for is another car coming into my lane that I need to move away from. But if there's nobody else there and the track is static, I should be able to drive it blind simply by remembering that area map, whatever they call it.
Right. So that was that when we started the first day, right? The first time that we had this meetup, that was what someone tried to do. I'm gonna cheat. I don't have any computer vision algorithms here. I don't have any TensorFlow. What I have is I'm gonna start driving the car and I'm gonna measure the time. Like I need to drive, I don't know, 5 seconds straight, then 2 seconds I need to be turning to a 20 degrees angle, and then you understand what I mean, right? Mm-hmm. So basically it memorizes the tracks, and basically it hard codes the tracks on the software. And you say, once I know more or less the distances at the time, the car will drive itself in circles, right? Doesn't work. And it doesn't work because the real world is not perfect and the traction is not always the same. So sometimes you tell your car to turn a 20-degree angle over 2 seconds, but depends on where it is, if there is a little bit of a slope or if it's taping there or the wheels are a bit more used, it won't really do 20 degrees, it will do 20 degrees, it will do 10 or it will do 30, right? So having just hard-coded maps is useless unless you support that with other sensors. So you always need to have the sensors, which is what real-world cars do. I work for a company called Mapbox that has that kind of data, which basically we provide tools for developers building any kind of mapping experience, and we have maps that tell you here's where the intersection is, here's where a tree is. This is all the data you need to know about where the car is, the surroundings, but you complement that data with sensors, because you never know if the car is raining and is moving slower or those
And
kind
also,
of
I
things.
mean, kind of like the backup plan, because my sense is that computer vision will take up more battery, because you're constantly using camera and processing frame by frame by frame, than something which is basically measuring accuracy against sensors for motion and depth. So I was curious.
Awesome. Questions?
Did you try, similar to the question, before you started computer vision, did you try like Bluetooth trackers or any internal like in-room out external sensors to improve tracking?
So, following on that example, if you don't wanna use computer vision that we're using it right now, or TensorFlow that we're using it right now, you wanna cheat a little bit more. Like you wanna, I know the tracks, I'm gonna just hardcore the tracks somehow. One way to solve the problem that I just mentioned, that you tell your car to rotate and it doesn't turn the angle that you want it, is you can connect it with a gyro, for example. So instead of telling your car, put this speed in these wheels for 2 seconds and hoping that that is a 20 degrees angle, what you can say is keep turning until your gyro says that you turn 20 degrees, right? But then you're going a long way for cheating purposes, right? You are now using sensors and hard-coded data to make your car being able to kind of drive in one scenario, right? At that point, just do it right. Just do computer vision or something else. And that's a good point.
So you showed a picture with the car and the dog and the ball. Did you use it to catch it? Did you train a model on the ball, or how did that work?
There's a question for Oscar. I don't know where he went, but he's going to speak about that in a second.
Okay.
That's another project built on these ideas for a different or slightly different purpose. And he's going to speak about that in a second. More questions?
Yeah. So you talked about route navigation. What about collision avoidance? Is that like the next thing for autonomous cars? Like how does it sees paths, which is what it was tracking, but suppose it were to go off that path?
So there are all kind of things that people are experimenting with it. Avoiding objects.
Mm-hmm.
You just put fake objects on the track and the car needs to be able to avoid them. And those objects are put randomly every time. So it's not, you cannot hard code where they are. Another one is following other cars. Imagine that you want to have like 2-3 cars driving together. And this is something that they said that it could happen with real world track driving. You have one human driving one car, one track, and then you have 5 tracks just following the human, right? So you only need, you don't really need to have autonomous driving in order to have autonomous cars. You just need to have one human telling others how to drive, right? So some of the people are trying that. Other people are doing this just for racing. So what they have, instead of tracks that look like a regular road, they have RGB tracks. They have tracks where everything is one color to separate like different tracks. And they use them to compete and try to pass each other. And they work on how to detect that a car is in front of you and how you want to pass the car and speed. So it depends on what you're interested in. Because this, at the end of the day, this is to learn. And
So this would be more like algorithms you do to like determine what your outcome should be. Like right now, the only thing you're doing is speeding up or sort of steering. You're not really speeding up and slowing down.
Correct. But it's totally up to you to experiment with that and implement it. If you ask me about what I'm interested in next, actually, I like to go to one of the ideas that I mentioned at the beginning, the fact that I can update the software of those cars remotely, that I can just push an update on the air, right, over the air, using the Android Things console. That's my secret master plan, to have a fleet of RoboCars that I can control remotely. But as we see more people coming to this meetup, some people, they really just want to play with them. They just want to like help you test the latest version of the software. So you can just actually like push the software before a meetup, for example, or before a racing event, and see how everybody does with different hardware, same software, for example. So some of the effort that we're going to put in the next few weeks, months is basically to make the project readier for this kind of over-the-air updates.
So let's say you wanted to add an additional function, like putting an arm on the current platform that you have. What steps would you go through, and how long would it take for you to incorporate something like that into the current platform?
So it depends on what you want to add, right?
So an arm that would grab something.
So
like a tool.
what you're gonna do is you're gonna need some other device. You're gonna need some other hat you're gonna put on top to control that additional piece of hardware, right? And ideally, it's something that we already have drivers for. If we already have drivers for it, it's almost trivial, right? Because you just put another hat, you just attach a driver to the code and just create your custom behavior. It's a bit more complicated if you need specific drivers for it. Actually, what Oscar is gonna talk about is a great example, because his camera, instead of being a static camera like mine, that is always the same position looking ahead at a specific angle, which is what you need for driving, what he did was to put basically a servo that controls the angle of the camera. So when you look at his control, he has a fancier version of this one with two joysticks. One of the joysticks controls how the camera moves. What he had to do was to add a new driver, and after that, you are good to go. And what we're trying to do is to make those drivers a bit more independent and easier to consume. So if you want to build your own thing that is completely unrelated, you can still do it. At the very back.
What's been done with outdoor driving, and what special challenges does it have?
So we haven't tried outdoors driving with these guys because they are too small for it. We care about them. We don't want them to get hurt. But everything that we are using in these projects is inspired or based on real-world algorithms. So if you are training yourself to be a self-driving car engineer, if you are doing one of these online trainings, for example, Udacity has a great training on how to do self-driving, how to become a self-driving engineer. If you want a platform where you can test all these real-world code and scenarios, this platform will help you with that. And everything that we use here is inspired by that. It's something that when you see the machine learning that we're using, the way we are thinking of convolutional neural networks, is because that's what real worlds do.
So let's say you wanted to move beyond, like if you were going into production, and you needed to move beyond Raspberry Pi or whatever, or how well does the code port over to like a generic ARM processor or other hardware like that?
Okay, so by the way, Nidia, you shut me up when I'm running out of time.
Yeah, you got 6 more minutes.
Okay. So I mentioned that a little bit at the beginning. As long as you are thinking of using any hardware that is supported by Android things, you don't need to change a single line of code. Because Android things provide an abstraction on top of the hardware so that your software can run very easily on any of those devices. Maybe I'm lying a little bit. Sometimes you need to change a few things because depending on the hardware board that you're using, sometimes the pin numbers change. But that's the kind of change you need to do. It's not like you need to change your algorithm completely because you compile for one architecture and now it's another architecture, right? So as long as you're targeting one of these platforms, you're good. If you want to bring your code outside those platforms, you want to build it to a generic board that is completely unrelated, I had no idea. I guess that it will depend. There might be some other boards out there that are compatible and it will make the transition easier. But you already play with this NXPP code. So basically, what you would do in the real world if you wanted to do this, and if there is someone here that is a hardware professional, please correct me if I'm wrong, but basically what you do is you prototype with this thing. And what you're gonna do is you're gonna extract this square here, which is what you have the CPU, basically. And that's what you send to production. And you are gonna print your own board that is gonna attach to the CPU. So after you have built your system, say you have a RoboCar that requires a motor hat and some, temperature sensor, and also requires to control a servo with another driver. You're gonna print a board that has only and just that component, those components, right? You're gonna print them in production and you're gonna attach it to a real processor. And that's what you would ship to production. And that's what Android Things is helping you with. Does that make sense?
Yeah.
Awesome.
On the software side, I didn't really get a chance to see exactly how you manipulate the drivers and what types of libraries get involved with actually controlling the motors and options servers and things like that. And I want to know how does that integration actually work?
Awesome. So I'm gonna give you the formal theory of how this works and then how we did it in practice. So in theory, the way it works, you have a new piece of hardware that you wanna support. Android will give you the basics elements to interact with the hardware. So Android Things is basically a stripped down version of Android with a bunch of libraries to access low-level components. Like if you are familiar with hardware, you're gonna have like PWM to control some kind of hardware, right? You're gonna have GPIO elements that is basically this low-level hardware access that you're gonna use to control them, right? All these libraries are provided by Android Things. Your job as an Android Things developer is basically to understand the different properties of your board and basically make it work using those libraries. How does that work when you are building a driver, for example, for a motor hat, for a project like this? The way we did it is actually we went and checked the drivers that were already existing for other languages. In this case, it's very common to see drivers for Python. So what you do is you check how the Python code works. And normally what it happens is just you have like several layers of abstraction, like the very low level that touches the individual pins and you're gonna basically write in bytes to specific registers. Then you have an abstraction on top that is more like, I'm gonna set this integer number as the speed of a motor. And then you have another layer of abstraction that is basically just move forward or just stop, right? And what the good thing about Android Things is that the very low level, you can remove it when you are putting those drivers because that's provided by the system. You don't need to bring in new dependencies. You don't need to worry about how that would work on Java, right? That is provided by the system. What you do is you use the basic libraries provided by Android Things, and on top of that, you just translate that into something that makes sense from the developer perspective. And normally using just porting on the drivers is a great way to learn. Or all the drivers that are out there provided by Google, they're all open source. So if you wanna learn how that works, how would you create your own driver for your own hardware, just go to github.com/AndroidThings, and there are plenty of drivers there that you can basically understand how that works.
And we're gonna take a break now, so we'll have a couple minutes. First, we want to thank our speaker. This was, I think, the longest Q&A I've ever had. So we're gonna take just a couple of minutes break if anyone wants to use it. Then we're gonna have Oscar. Oscar doesn't even need slides. He's literally gonna drive this thing around.